Hey guys, I just want to do a quick video about resonance and coils. Resonance and coils consists of, it would typically be LC resonance, which means L is the inductance, C is the capacitance. The capacitance comes from the distributed capacitance between the turns. So for every turn that's on the coil, as the turn is as close to the turn that's next to it, there is a capacitance between the turns. So for each turn, the capacitance would grow, and you end up with a coil that has not only inductance and resistance, but it also has capacitance as well. And that's the same with a lot of components in electronics. An inductor is not always just a pure inductor. It does have resistance, does have capacitance, and that's much the same for many components. They all have a little bit of each other in them, some not so much, some a little bit more. Anyway, resonance, magnetic resonance. Magnetic resonance we've defined on the website as 180 degrees out of phase from each other. So if you have two coils, the two coils are in resonance, the two coils must be 180 degrees out of phase. So one is moving one way, one's moving the other way. So this is the standing wave that we were talking about. So effectively, the waves, the magnetic waves, are equal and opposite, 180 degrees out of phase. Alright, what I want to show very quickly is the circuit that we're going to be using. So we're going to try and do this while we're actually connected. So I'm going to very quickly try and throw this together. If my little friend over here be's a little bit quiet. So we're going to tip that on its side, tip that on its side. Whoop, wrong way. Okay, so this is the circuit, the basic circuit that we're using. Now it's very simple. The inductances are not the same, but we will change that in a minute. Now, so just have a quick resistor. So what we're doing here is we're really just showing you what I'm doing, and this is the simplicity of the circuit. Now the circuit itself carries very little current. There's very little current in here. We don't have a connection on this side here, and we will actually mark that as not connected. So we'll grab a couple of connectors, tip them on its side. Okay, and we are going to go NC for not connected. Okay, we're going to copy that, copy, paste over here. Whoop, there we go. Oh god, that's terrible. There, okay. Alright, so this is the circuit. Let's move it in the middle of the screen so we can see it. Okay, so over here we have a this is just a simple, very simple function generator. The function generator itself it's not grounded, so we basically have no real current from the function generator. The current is, as I say, excuse me, it's not a closed loop. So L1 is going to be the primary coil. Now what we're going to do is we're going to change the value of that so you can see that that value is real. Okay, and what we're going to do is we're going to throw some probes on here just to say that probably shouldn't have done that, but anyway. So we're going to throw some probes on here just to say where we're measuring it from. So this is going to be red. Okay, actually this will be scope earth. We'll spell it right, hey? GND. Scope ground. Grab another one. And this one here is going to be yellow. Okay, so you can see the simple circuit. Again, function generator, primary coil, have roughly about 180 turns on that coil, but the inductance and everything like this for this video doesn't really matter too much. It's really just showing you what we're actually doing. Okay, so the coils are not connected to each other except for the earth on one side, so there's no current that would be flowing through each other. L2 over here is a similar coil to L1, nearly identical, probably not exactly, there might be a tiny little bit of difference in inductance. Again, this is the current measuring resistor over here, non-inductive, just a metal strip resistor, metal strip through hole resistor. And I'll show you in just a minute what we're doing now. To give you a bit of an idea of what we're actually doing here, is we are finding a frequency on the function generator to bring L1 and L2 into resonance. Okay, so we're going to find the resonance on L2, so we're measuring on the scope. This is the red channel, this is the yellow channel, and that's the scope earth. So we're measuring on the red channel and yellow channel when this coil becomes resonant. Okay, and what we're looking for is we're looking for the maximum amplitude that we can find when we are pushing this coil to push this coil. Okay, so effectively this is, you could say at least, this is magnetic, electromagnetic induction between the two coils, but the difference is that it's at a resonant point. Okay, so I'm going to show you that experiment now. We'll have a quick look and hopefully it all makes a bit more sense. Alright, so this is the basic setup. We've got two coils, so this is the coil that we're putting an input signal to. The input signal is going all the way up through the coil, back, and then it's coming back again to the, so this is a resonance. So we're putting an AC signal, just a positive AC signal here, all the way up through the coil, up to here, and then it's coming back again. The middle coil here, we're not driving at all, that's not connected. This is the other coil. Now I want to make a very clear point. These two here are the partnered output coils. Okay, so these are the resonant coils that we need to focus on. Okay, and the magnetic interactions between these two coils, the magnetic interaction between these two coils, are what creates or pumps or pushes the electrons down the wire. Okay, what we're going to do is we're going to see in a minute a little antenna theory trick that I learned from a very good friend of mine, and we're going to go through and sort of show you I'm going to go through and show you the basic ideas here. So remembering our circuit that we just drew, okay, so we've got one coil that we're bringing to resonance, and we're checking the resonance over here on this coil. These two coils are nearly identical. Okay, so turn for turn they should be the same. The only difference would be the slight difference in the resistance of the wire. The wire quality might be a little bit different, so therefore the inductance, resistance, and so on might be just slightly different, but the coils themselves are nearly identical. Okay, so red probe here, that's measuring the voltage. Okay, on that terminal, we're measuring a current that's coming out over here through our, this is our metal strip resistor, 0.1 ohms. Again, probe is set on 1. If we go into the scope, okay, channel 2, we're looking at a 10 times coupling in there. 10 times 0.1 is 1. So if we're looking at V equals I over R, the resistance 0.1 times 10 is 1. So 1 volt through 1 ohm is 1 ampere, if my brain is clear enough and thinking properly. So there you can see the calculation. Alright, so yellow trace, yellow probe measuring current, red trace measuring voltage, and you can see on the scope there, it's a bit hard, it's not triggering properly, but you can see on the scope there we're getting a waveform. Frequency at this stage we're looking at just over 3 megahertz. Okay. Now I want to go through and just explain. You can see that the current and the voltage is out of phase, and it's well out of phase. It's more than 180 degrees. If we use the cursors, if we don't be silly about it, go back to cursor. Okay, so a wave period. Oops, a wave period here. Okay, so wave period is 2.96 nanoseconds, 296.0 I should say. Okay, and if we go back to the current, that's 200. So our calculation according to this, just a very rough calculation, this time of night we're looking at a degree angle of 243.2. Okay, that's just a very rough calculation, and that's the phase shift between the voltage and current at this particular frequency. Now I want to point out that this frequency is a, get the thing, just knock it and it goes funny. So I just want to point out at this frequency we are looking at a voltage and a current phase angle difference, but also what we're looking at is we're looking at a harmonic, if you like, if you want to call it harmonic, it really is. At least this is a harmonic interval of the resonant frequency. This is not the resonant frequency of the voltage. What I want to do is I want to show you that now, so we're going to crank this down a little bit. We're going to turn channel 2 off, go back to measure, and we're going to play with the frequency on the function generator. I'm going to wind it down a bit, a little bit more, and you can see there, we're getting a much bigger amplitude, so we'll wind that down. Much bigger amplitude on there, and our maximum amplitude, let's try and find exactly where it is. It's about there, isn't it? So the maximum amplitude for that setup is about 131, so 132 kilohertz roughly. Let's try and peak that a bit better. There's 131 kilohertz. Let's see what we get on the cursor. So, whoops, I always do that. Back to cursor. So we'll go peak to peak. That there is telling us 131.6 kilohertz. Now I just want to make a point at this stage and say that this is the maximum voltage that we're getting on the coils in this resonant setup. Okay, so voltage, we're looking at an amplitude of voltage, okay, at this particular frequency. I want to remind everyone that if we don't have resonance, we lose our voltage amplitude. It's really important. If we get resonance at the resonant point, we get voltage amplitude, and voltage is critical. Okay, that's why resonance is so important. So what we're saying is that these two coils here in this setup, and remembering it's open circuit, we're not driving a current through it, this is open circuit. So we've only got one connector there from the function generator, pushing a sine wave all the way through here and back again through this coil. and this coil is coming into resonance, we're finding the resonance frequency on this side, and this is voltage. So we're looking at voltage at this stage. Remembering that current is V over R, voltage over resistance. Okay, so the higher that we have a voltage, if the resistance stays the same, then the higher current we will have go through the load at the same time. Okay, so what we've found here is we've found the maximum amplitude of voltage for these particular coils. Okay, now the two coils again, the two coils are the same. So basically one coil would mirror image the other. This is, if you like, the part and the output coils themselves have a symmetry to them, but the overall machine is asymmetrical. We're looking at asymmetrical regauging in the machine, and I'll show you what's going to cause that now. So what we're effectively doing here is, by finding the maximum amplitude of the coils, we're finding the point at which the coils if you like to have a magnetic resonance between them. So it's electromagnetic induction between the two coils. One coil is causing the other coil to come into resonance via electromagnetic induction. Okay, and what we're looking at here now is a quarter wavelength. What we'll do is we'll make it a bit bigger so you can see. Okay, so the quarter wavelength is from 0 here to the peak. Okay, so what I want to point out here is, between the two coils, what we're looking at is we're looking at a rise over run, which is the steepness. Okay, so rise over run, and the run is the time. Okay, so in this particular case we're looking at 2 microseconds per division, and we're right on division. So what we want to do is we want to have a coil, an input coil, that is driven at roughly about 2 microseconds worth of pulse for these particular coils. The resonant frequency determines the quarter wave. Okay, and this is something that Don Smith told us as well. No one's really picked up on it.
Now, one of the problems that people run into in building these things is getting the two coils to react with each other. You've got to have them so that they can talk to each other. So if you use like quarter wave system, your shortest wave will be the longest length of wire, and your shortest length of wire will be your higher frequency.
But again, Don Smith told us about it, Russ Lane told us about it, Akula told us about it. They've all told us about the resonance period, okay? And the quarter wave is so important, okay? Because our aim, our goal, is to get the amplitude up of the voltage. Okay, so this is a very, very steep rise over that particular run. Gets the voltage up to a maximum at these particular coils. Alright, so what I will show now is we're going to keep our quarter wavelength, and what we're going to do is we're going to have a look at the asymmetrical regauging. Okay, so our time period here is very, very important. So we're going to regauge, okay, which is now maximum amplitude, and then after the regauge we have a work period. Okay, so the coils interact together. They've got a maximum voltage, they are connected to a resistance, so a current will flow, and the current is going to flow because it's being pumped. One coil pumps the other coil. Remembering we've got a voltage up as high as we can because it's in resonance. Okay, and then the voltage pumping, or the current pumping, is basically the linear decay of voltage and current over time through the particular resistance. Right, and that's why we get a linear decrease, and that's the work period. Now the work period might be quite long, depends on your system, depends on your setup and your coils and your inductance and stuff like that. Unfortunately, I still don't have the exact math, equations, all that sort of thing. I'm trying to share what I've learned. So basically at this stage you just have to take my word for it. But if your gut feels right and you see what I'm sharing as true and correct, then I urge you to follow these experiments, do them yourselves, and get this effect happening. Again, the voltage up, okay, V over the resistance, okay, over R is the current. So V over R is the current, which is seen as a linear decay. Now, remembering at this stage, the first rule of electromagnetic induction, okay, is the time rate of change of the magnetic fields. Okay, so if we're in resonance, we have equal and opposite magnetic fields in resonance. The coils are going to have a very, very, very low impedance. Okay, remembering the impedance is XC and XL. So if XC and XL are equal but opposite, they cancel each other out. So from 0 to peak, we have no impedance, okay, because it's in resonance. So our coils have 0 impedance, possibly even less sometimes, could go negative. So we have 0 impedance during this rise time because we have resonance. Okay, so we're getting our coils up to a maximum voltage because of the resonance, that's the amplitude, and then we switch off our input. Okay, this input is this period here, switch it off and let the coils go. And this is exactly the same as placing the magnet at the top of the copper tube and then letting the magnet drop down the copper tube. Okay, so this is the drop down of the magnet in the copper tube, and you know that can be very slow, so sometimes that might be way out here. So your frequency overall could be very low, but you need a very short duty cycle in here. The duty cycle in here is very important, okay, to get your coils up to maximum amplitude and then switch it off and let your coils go. Okay, this is bucking coils, this is partnered output coils. Okay, so once you get these effects happening, you're home and hosed. This is the answer, guys. This is everything. I'm probably rambling at this stage now, so what we might do is we might get this video up. Please understand how important this is. Once you get to the stage of something like this, it's a very short pulse on the input coil. Again, this input coil here is not connected, it's not doing anything. But these two output coils, partnered output coils here, 1, 2, now that they're in resonance, we know what frequency they like to see, okay, because that's the key. Maximum amplitude, sorry for the shaking. Maximum amplitude, we have maximum voltage, and then we switch off and we let the coils pump current for as long as they can. Now the pumping of current, I'm not able to calculate any of that sort of stuff. This is where I'm a bit lost. I'm sorry guys, I really tried to get to this stage, but I'm sort of lost. There's so much to it, it's so complicated, I just can't give you all the answers, unfortunately, but we will get there. So what I'm sort of trying to say here is get your voltage up on your partnered output coils, which is the switching, okay, which is the frequency and duty cycle, and also voltage. You might want to just push your voltage up just a tiny bit on your input coil to get your voltage up on your output coils. Switch it off at quarter duty cycle, okay, so input coil switches on here, climbs, switches off. Remember, your input coil has to have very few turns on it, has to be a quarter wavelength, okay, because that's quarter wavelength. Go and visit all our antenna theory threads. We've got lots and lots of data on this on our website. Okay, so input here, switch it on, let it rise to maximum amplitude, and then drop your input, let your partnered output coils do as much work as possible. This is your work period over here. Remember, asymmetrical regauging, go through, read it, study it. We've got a regauge period, which is the switch on, and then a work period. Okay, your work period is going to have a lot more energy in it over here than what your work period over here, sorry, your regauge period over here will have. Alright, I'm going to get this up. Remember your partnered output coils, they've got to work together. They pump current electrons. Once they're free, once they're excited, they have a magnetic field. All you have to do is push them down the wire, and that's done electromagnetically. Okay, magnetic field changing in time pushes your electrons down the wire, and then you have a current.
The devices which I have invented, which there are a number of them, they all actually accelerate electrons.
Okay.
They're electron accelerators, and